there aren't any questions, we will move into the Riemann curvature tensor. So finally, we're going to have today our invariant characterization of what it means for a space or a space-time to be curved. We've hinted at this a number of times in a number of different ways. And there's three ways you could talk about the Riemann curvature tensor. It could actually be defined using any one of these three ways, and then the other two could be derived. But it's good to just tell you what it does. So one thing that the Riemann curvature tensor characterizes is the failure of a vector to return to its initial value when parallel transported around a closed loop. So we drew cartoons of that, and this is also a way you can define the Riemann curvature tensor. So in this case, the Riemann curvature will take the closed loop to be very small, kind of like in the commutator problem when you took a closed loop to be very small and asked about just where you end up after following integral curves. So the idea here is you have two vector fields, call them A and B, at a point. So here's one vector field, A mu. Here's another vector field, B mu. And you define a loop, which is the same type of thing we did for the commutator. This is also B mu. This is also approximately A mu. And you parallel transport a third vector, call it V. You parallel transport that around the closed loop. And when you're done, you might come back to some other vector. It might look like this. This might be the final value of V. Final vector after parallel transporting V. Okay, so it could be different. And then there would be a small change between the two, like this. That would be delta V, if you like, in green. And then the formula, delta V mu, is going to be linear in all these things because we're going to keep to leading non-trivial order as the loop gets smaller. And so the small change delta V for an arbitrarily small loop is going to be a linear map. I use the index rho for consistency with my notes. So it will depend linearly on the initial vector, which I'm going to write here as V sigma. And it will also depend on A mu and B mu. So I'm going to call those A mu, B nu. And then what can I put here to make a linear map? Well, I've got one upstairs index rho so that I match my delta V. And then I need to just have indices to eat this up. So rho sigma mu nu. So this is one definition of the Riemann curvature tensor, which naturally lives with one upstairs index and three downstairs indices. And the convention we're using, which is pretty much universal these days, is the one given here. But of course, we'll be raising and lowering indices freely, and many of the properties of the Riemann tensor are easiest understood with them all lowered. So the up-down is just a convention for thinking about this particular definition of the Riemann curvature tensor. Now, we're not going to take that as our definition, and I'm not going to go through, and when we define it another way, I'm also not going to derive this equation. But you can imagine how it would go if you did the parallel transport problem. It's a very similar thing. You just have to write out a lot of terms and show that this rank 4 tensor is the same thing we introduced in one of these other two ways. But conceptually, this one is very important. Right? Remember the example of a sphere where we parallel transported our vector around a big triangle right? A triangle made of all great circles, all lines that cut the sphere in half, and it had 3 right angles in it, and we saw very visually why the vector wouldn't necessarily return. In fact, in that case, wouldn't return to itself after parallel transport around that loop. And that was some signature that the space is curved, and this is making it precise and local by shrinking the loop arbitrarily small and thinking about the leading order failure of parallel transport around the loop, and that gives a local notion of curvature. Yeah. It does. That would do a sign flip if you went. So I've drawn here, you go first along A, then along B, then along minus A.
How is that reflected in your equation?
It's reflected in the anti-symmetry of the Riemann tensor in the last 2 indices, which I haven't derived yet, but that follows from the fact that orientation reverses and you get a sign flip, so the Riemann tensor must be anti-symmetric in the last 2 indices. Good question. In fact, let's just write that down. Interchanging B and A flips the sign as the orientation changes. So it follows our first symmetry property of the Riemann tensor, Riemann sigma nu mu equals minus Riemann rho sigma mu nu. In other words, it's anti-symmetric on the last 2 indices. We'll actually see that when you lower the first one, it's also anti-symmetric on the first 2 indices. We're going to see that algebraically, not by a slick argument like this. Okay, so that's one of 3 ways we could talk about curvature. The second way is the failure of initially parallel geodesics to remain parallel. So at least when I took geometry in high school, there was a big deal made out of Euclid's parallel postulate. And so by the failure of Euclid's parallel postulate can be used to characterize curvature. So you can also think of that, the cartoon here is just you have 2 geodesics, but eventually they won't be parallel, they'll converge or diverge. And you can also see this very easily on the sphere. One thing that you'll encounter on the homework, if you haven't done it yet, is that the geodesics of the sphere are the great circles, the things that cut the sphere in half, like the equator or any longitude line. And so if we just draw 2 great circles, such as, this one, there's a great circle, and this very nearby one, and, you can see they actually started at a point. So if you started them roughly parallel, here, they would converge if you went that way and diverge the other way. And actually, they'll converge again when you reach this pole. This one we will derive, something called the geodesic deviation equation. It's not a terribly useful equation in practice. In fact, it's led to some confusion. I very much like the book, but I did find a slight error in this book in a later section where there was an invocation of geodesic deviation that was somewhat imprecise. And in general, I haven't found a situation where it helps to use this in practice. But conceptually, it's important to think about what gravity does locally. If you start it's like a tidal force, right? It separates things a little bit. You can characterize that in terms of a space-time version of failure of Euclid's parallel postulate. And historically, this type of thinking was very important, for example, for people understanding that gravitational waves were a real phenomenon and not a coordinate effect. It was helpful to realize that you had this geodesic deviation equation which told you that your gravitational wave detectors would move locally based on an invariant thing, the Riemann tensor, and not some coordinate-dependent calculation. All right, and the one we will use to define the Riemann tensor is failure of covariant derivatives to commute. So we took a torsion-free assumption, which said that covariant derivatives commute when acting on scalars, but when acting on higher rank tensors, they won't. And so our definition of the Riemann tensor will be del mu, del nu, v rho, minus del nu, del mu, v rho, equals something acting linearly on v. So we need, again, an upstairs index to absorb the rho. We need a downstairs index to absorb the mu and the nu, and we put those last in this definition. And then what's sitting here? Well, we have to have some dummy index contracting with v. Okay, so this is going to be our definition. I'll put colon equals, or maybe it's better just to write defines Riemann tensor. And we will check that this is a good, useful definition simply by deriving the formula for the Riemann tensor in a coordinate basis. Yes? No, the Riemann tensor includes Newtonian gravity. So tidal forces in your lab, you can still measure in Newtonian gravity. The equivalence principle is already true in Newtonian gravity, right? If you're out in an elevator, you can't tell if it's gravity or it's accelerated frame unless you notice that the two test particles you drop or whatever converge towards each other because they're both going to the center of the Earth. So that tidal force is there in Newtonian gravity. And the Riemann tensor measures that convergence of two different, it's the initially parallel geodesics no longer remain parallel idea. So the Riemann tensor is the leading effects of gravity when gravity is small, but that includes Newtonian gravity. But it also includes non-Newtonian gravity. If you work out the Riemann tensor near a black hole or something, that will tell you the leading effects of gravity in the small laboratory near a black hole.
So in Newtonian gravity, we expect these covariant derivatives to not commute?
Yeah. The only time they commute is if there's no gravity at all. Space-time is flat, but that's no gravity. We will do the Newtonian limit a little later. Once we have Einstein's field equations, we will take the limit where gravity is weak, and we will see how all these things, covariant derivatives, Christoffel symbols, give us back the phenomenology of Newtonian gravity. Let's use this to get a formula for calculating the Riemann tensor, which I will make you do once. It's a big pain to calculate these things. But I'll only make you do it in 2 dimensions, but it'll still be a big pain. Okay, so let's derive a formula for R. So the first thing is to recall that these covariant derivatives do commute when acting on some scalar phi. But of course, it's not going to be true for vectors. I just wrote that above, but let's emphasize it with the not equals. And similarly on higher rank tensors. So now we'll just calculate this commutator. So let's just, well, not a commutator of vector fields, a commutator of derivatives. So let's just calculate. Okay, so when you have these 2 covariant derivatives, it's always good to work on the outer one first, because you only know the formula for a covariant derivative acting on a tensor. And if I expanded out this inner one in terms of partial derivatives and Christoffel symbols, I wouldn't know what to do because I'd have this equation with covariant mu acting on partial nu. I don't know how to expand that out. So we go from the out in for this kind of equation. So the first thing we do is we write partial mu of this tensor, del nu v rho. And then I'm working on the first term here. And then there's a Christoffel correction with got 1 down and 1 up. So we're going to have 2 terms. First, the downstairs one, the Christoffel comes with a minus sign. The mu goes here. The nu is replaced by, oh no, the nu goes there. No, I'm working on mu, right. Nu is part of the tensor. So that moves here on the Christoffel, and I'm working on the first index. So this must be some dummy index lambda. Then the tensor is covariant lambda, and the rho just goes along for the ride. We're not acting on that yet. And then I have the second one where I am acting on rho. I get a plus. And then again, mu is down here. That's the derivative index. Now I'm going to need my dummy down here to be contracted with my upstairs dummy index on v, and what is left must be rho. Del, I need the del. Okay, and then I could write out the other terms, but I'm just going to write minus the same thing with mu interchanged with nu. Okay, so that means all 3 terms, I just take each one and I add a term with the same thing, but I've swapped mu and nu, because that's what we have on the left-hand side. So that notation will save us a bit of time. Now, I can expand out the inner ones. So let's go ahead and do that. So del lower mu. Now we have to expand out this one. Partial lower nu v rho. This is an upstairs index. It comes with a plus rho mu nu. Whoops. All right, that looks good. Now I have a minus lambda mu nu, and I do the same thing, del lambda v rho plus rho. Now I've already used lambda, so I'm going to need maybe a sigma as my dummy index. Maybe, but let's just go in order. Rho mu lambda, and then this is partial nu v lambda plus Christoffel. I guess I have an upstairs lambda now, a downstairs nu, and another sigma. And all this minus mu interchanged with nu. All right, so did you see some things canceling, Evan? Yeah, I can't argue with you. So it was 0 already here, because this term is symmetric under mu interchanged with nu. And we're subtracting off the opposite thing, so it will cancel with the mu interchanged with nu. And the other terms are symmetric? Yes?
The very first term will have partial mu, partial nu, but those can commute.
Exactly. Partial derivatives commute. So for the same reason, this term, because this term is del nu v rho, also symmetric, del nu del mu v rho. So that will have another term with minus mu goes to nu. That will cancel. So I see del mu acting on, I'm going to write one term with it acting on the Christoffel. So my notation is it doesn't act on v lambda. But then I'm going to also include that term, nu lambda del mu v lambda. And then I'm going to have a term plus gamma rho mu lambda del nu v lambda plus gamma rho mu lambda gamma lambda nu sigma. It's fun to say a string of 8 Greek letters and hope you know what I mean. V sigma minus mu goes to nu. All right, do you spot anything on this line, Evan?
The middle two terms, when added together, are now symmetric under mu.
So notice that these two together are symmetric under mu goes to nu. So again, they're going to get added with another term where we do the thing with mu and nu interchange, but with a minus sign. But those terms are the same because of the symmetry. So indeed, this whole thing goes away. And that actually is very, very, very important for showing that my claim that I defined a nice Riemann tensor is correct. Because these are the terms with the derivatives acting on v. If you go back up to what I claimed was going to define it, I claimed it was going to be linear in v. There weren't going to be any derivative of v terms on the right-hand side. So we see now that that works. I'm sure there's a more elegant way to see from this and the definition, the properties obeyed by covariant derivatives, that that's true, but this way we see it computationally. So the derivative of v terms cancel out. And now we have our final expression. I'll go ahead and add in the minus mu goes to nu terms. So we'll have del mu gamma rho nu lambda v lambda minus del nu gamma rho mu lambda v lambda. So that's from the minus mu goes to nu of the first term. Plus gamma rho mu lambda gamma lambda nu sigma v sigma minus gamma rho nu lambda gamma lambda mu sigma v sigma. Good idea. Because that was our definition, to write all this thing in terms of something times v lambda. So let's pick lambda here. So let's swap lambda and sigma on both of the last terms. And then we can factor out the v lambda. So we'll have del mu gamma rho mu lambda minus del nu gamma rho mu lambda plus gamma rho mu sigma gamma sigma nu lambda minus gamma rho nu sigma gamma sigma mu lambda all times v lambda. Okay, and so this then is our formula for the Riemann curvature tensor. And by the magic of technology, I will copy and I will write Riemann rho lambda mu nu, that was our definition from above, equals that. And if I can get it, yes. It's the sloppiest of the writing, but because I was going fast at that point, I was getting good at it. Right, so that's our Riemann tensor formula, because this thing here, by definition, was just Riemann rho lambda mu nu, if you go back to the definition I gave. Okay, so this is part of the proof that it does define the tensor. If those partial derivative of v terms didn't disappear, it wouldn't have worked. But more importantly, this is how you calculate the thing. It's a pain, yeah. Any questions?
On the bright side, we only have to find 16 components.
I think there's 20, but I haven't told you all the symmetries yet, so you don't know there's only 20.
Well, no, I'm talking 16 because you said we're only calculating it in 2 dimensions.
Oh, in 2.
I guess.
Yeah, there'll be even fewer. There'll be even fewer in 2 dimensions. Okay, we're good on this? So, I mean, it's a bit of a mess, but, you know, there'll be messy calculations with indices on homeworks too, so hopefully you see some of the techniques and tricks.
So, I mean, in terms of symmetries,
We'll get to the symmetries.
I'm guessing it's anti-symmetric.
Well, let's just wait. We'll get to them in 10 minutes or so. Okay. So, some comments. First of all, if I didn't think geometrically, remember these 3 definitions were all in terms of clear, either geometric pictures, drawing pictures, so you know this thing doesn't depend on the coordinate system, or using covariant derivatives, which we laboriously constructed so it doesn't depend on the coordinate system. And that is why we are guaranteed that when we're done, that we get this tensor out that is a good formula, that this formula really holds in any coordinate system. Okay, you can calculate the components of the Riemann curvature tensor by getting the Christoffel symbols and then doing these contractions and derivatives. And that is totally not obvious from this formula. Right? If I just started with this formula, I said, good morning, the definition of the Riemann tensor is, and I wrote this out, you would have absolutely no way of telling whether this was a good formula that obeys the tensor transformation law or just something I randomly made up, right? So it's not at all obvious from this form that this thing R lambda mu nu obeys the tensor transformation law. And if you were tasked to invent a local notion of curvature, you would say, okay, it needs to be a tensor. That's the machinery we've established for formulas that hold in any coordinate system. It would not be a good strategy to just start trying random combinations of Christoffel symbols and their derivatives, right? So there's a lesson here that thinking geometrically is important. So geometric or invariant, sort of the same idea, is crucial. Okay, you could never have guessed this. Okay, I already said this in words, but notice the importance of the derivative of v terms canceling out. We need that so that Riemann tensor defines a tensor, right? This equation R v is like the commutator of covariant acting on v, works to define a tensor. Right, there's no room for a derivative of v terms there. And finally, well, this isn't really common. This is part of the main development. We also need to know about other tensor fields, like one forms. So what about a one form omega? Well, we're going to have the same equation, del mu, oops, do the same thing, del mu, del nu, omega rho minus del nu, del mu, omega rho. And I'm going to tell you the answer, and then we'll check it. Minus Riemann lambda rho mu nu omega lambda. So this has a familiar flavor from the Christoffel symbol stuff. We defined the Riemann tensor in terms of how covariant derivatives acting on vectors fail to commute, but they fail to commute precisely by a linear map on the vector, not including the vector's derivatives. And it'll be true for every other tensor that except for scalars, that covariant derivatives won't commute. And it's just a sort of permuting of signs on the Riemann tensor. You get a permuting of indices together with a minus sign. These ones don't come up as much, so you don't really need to memorize them the way it's helpful to memorize the Christoffel symbols. But there will be calculations probably on this week's homework where you have to use this kind of identity. One sec. And then for higher rank tensors, it's just like Christoffel symbols. You just add one Riemann term for each index in that tensor when you do the commuting of its covariant derivatives.
So does R have the property where when you raise or lower, when you swap the upper index with one of the lower indices, it picks up a minus sign?
I wouldn't swap upper and lower indices, but it is going to be true that when you lower the first one, it's going to be antisymmetric on the first two. I don't know how you see that from this equation. It's possible you could. I haven't derived this yet. I'm just putting the formula clearly, and then I'll show you how to check it. Okay, and then similarly for higher rank tensors, higher rank is just one term for each index. So for example, Let's see if I can do this. Let's do a one with one upstairs and one downstairs. So del mu, del nu, t rho sigma. Let's do that. See if we can get it right. So minus del nu, del mu, t rho sigma. There's going to be two terms. They're both going to say Riemann with 4 indices, t. And one is going to come in with a plus sign because that'll be the upstairs index. Another one is going to come out with a minus sign because it's a downstairs index. Since we have the formula for the minus sign here, let's work on that one first. We can see from the formula that the lowered index on the omega gets transported to the second slot of the Riemann tensor. So here the lowered index is sigma, so that's going to get transported to the second slot. Never leave enough room. Sigma. And what else? Well, the mu and nu just hang out in the last two slots of the Riemann tensor. And then we have a dummy index here that was called lambda, which is going to go on top of the Riemann tensor and in the slot of the tensor we're working on, which is the second one. And then the rho is just going along for the ride. So right, it's very similar to the game with Christoffel symbols. And then for this Riemann term, now we're working on the first index. As before, mu and nu hang out in the last two. The first index is a rho, so that's going to become up here. And then we're going to need a dummy index lambda up here. The sigma just goes along for the ride, and that means I must put a downstairs lambda there. All right, is it clear? Hopefully you've done enough Christoffel calculations that this doesn't look totally insane. Yeah?
So like for the first term, like for the R, so basically if you notice above, like the lower index on omega went to the second slot in R, right?
Mm-hmm.
So, but in like in downstairs, the lower index is sigma on both of the T. So shouldn't be the second slot be sigma again?
Here?
No, like why is there lambda?
So we're working on, you think of each term as kind of working on one index. So in the first term here, we're working on the rho index.
Mm-hmm.
And so the rho index is going to leave the tensor and move over to the Riemann. So whereas rho was here on the tensor, it got moved over to the Riemann. And then where rho was, we put a dummy index lambda. And then it has to contract with the downstairs index on the Riemann tensor. I don't know how visible that is. Does that make sense? And then for the second term, well, now we're working on the sigma. So the sigma gets changed to a lambda or at some other dummy index. And then it has to contract with an upstairs Riemann. And then the sigma ends up on the downstairs Riemann slot, and mu and nu go along for the ride. You're going to use this once or twice, but then never again. It's not as universal as the Christoffel formula. It's just conceptually, it's important that the Riemann tensor is encoding the failure of covariant derivatives to commute on any tensor, except for scalars where they do commute. All right, let's check this one. So let's check how this works. So it's the same game we did with Christoffel symbols to promote from our initial Christoffel symbol on vectors to our one forms. We just consider the contraction of some vector and some one form. And we use that, just like there's no Christoffel symbols for scalars, there's no Riemann tensor terms for commutation of scalars. And so we'll compute this thing, some omega rho v rho minus mu goes to nu. Let's write that a little better. So this thing has to be 0 because scalars the covariant derivative does commute on scalars. And then we can use the Leibniz rule. I seem to have used it for second derivatives, which makes me a little suspicious. So let's go really slowly. You guys can help me. So del mu acting on del nu omega rho v rho plus v, wait, that looks terrible. I don't know if that hurts your eyes like it hurts mine, seeing two upstairs repeated indices. Yeah, you can just shout that out if it burns your eyes. Okay, del nu omega rho v rho plus omega rho del nu v rho minus mu goes to nu. And then let's keep going. Del nu omega rho v rho, so these derivatives are only acting on omega rho, plus del nu omega rho del mu v rho plus del mu omega rho del nu v rho plus omega rho del mu del nu v rho. Okay, let's look for places we can use our Riemann tensor equation. Is this green hard to see? It's a little harder for me to see. Looks okay for you guys. Yeah. It's possible it's wrong. I just used the Leibniz rule on this del mu. So this del mu del nu acts only on omega nu. But then I have the case where del mu acts on v rho. And I still have del nu omega rho. Yes?
How is this checking the commutator on one foot?
We're going to get there. You're going to see it pop out.
You're starting with checking that on a scalar.
I'm assuming that's part of the definition of our metric compatible derivative was that it commuted on scalars. That was the torsion-free condition.
Okay.
So I'm using torsion.
You started with a scalar, but we're building towards.
Yeah, it's going to happen quite shortly. Anyone see what I should do? Remember, there's minus mu goes to nu here.
You have a bunch of commutator terms, like all the
Yeah.
del mu.
Right.
Plug the Riemann tensor.
Well, I don't know the formula for this yet. I'm going to derive it. But this one here, right? So this thing here, when I include the minus mu goes to nu, this is the commutator of mu and nu acting on a vector field. So let me write that in red. Yep, that's going to happen too. So let me first write this out. So this red thing is going to become omega rho del mu del nu v rho minus del nu del mu v rho. That's the red thing when I include the minus mu goes to nu, and then these are going to cancel, as Peter just pointed out, because this thing here plus this thing here is symmetric under mu goes to nu. Remember, you can freely, I don't even have to freely raise and lower. It's just manifestly symmetric. It's the nu mu term added to itself with mu and nu interchanged. And so that's going to become 0. That's just gone. And the first term is, well, what we're looking for. This is del mu del nu omega rho minus del mu omega rho, all contracted with v rho. That'll be purple. Okay? And so then this thing, by definition, over here was the Riemann tensor rho lambda mu nu v lambda. Now I'm getting wacky with the colors. Times omega rho. That's horrible. Switch to red. Omega rho. And then this thing is what we're interested in, right? So let's just move that to the left-hand side. And we'll just say that this is now, let's move the Riemann one to the left-hand side. So we have the minus sign there. And then this one is just del mu omega rho minus del mu omega rho, all contracted with v rho. So it should now be obvious. This has to hold for any vector v. So maybe to make it obvious, I'll switch indices here. I'll write this as minus omega lambda r lambda and then rho mu nu v rho. That's just relabeling indices. And so now you see the v rho multiplying both hand sides, but we want this to hold for any v rho, not just some specific v rho. And so we then get our formula. So holds for any v rho. So we can just peel off the v rho and we'll get what we want. Del mu omega rho minus del mu omega rho equals minus Riemann lambda rho mu nu omega lambda. And hopefully that's what I told you the answer was. Okay, so you could imagine repeating this for higher rank tensors, and you would just find what I asserted, that if you have a rank 6 tensor with 6 indices, you commute the covariant derivative on it, you get 6 terms, each with the Riemann tensor, with the indices lining up in the only way they could. As long as you remember the last 2 indices are the ones where the derivatives appear, and then just minus sign for one forms for lowered index and up plus sign for upstairs index, and you can write out all the terms. All right, this is not fun. I mean, if you think this sort of puzzle is fun, then this stuff is fun, but this is not fun for me. And I'll ask you to do one fairly annoying calculation this week, which will be, if you succeed, it'll be your gold star certification as a tensor mechanic. But it's just comes with the territory. Questions? All right, here's a nice theorem. I'll do one direction. The other direction is in the book. I know better than to parrot the book's arguments in front of all of you. Yeah?
One thing, like, if, for example, that first term, like del mu, v rho, omega rho, can we use chain rule on that also, like?
Chain rule where?
Like the first term, like del mu,
This?
mu, yeah. Like, so basically right now del mu.
Well, what the chain rule would be like if we were changing coordinates or something.
Like, right now del mu is acting on del mu v rho, right? Omega rho combined.
Yeah.
So I just say that it's del mu, and then just v rho comes out, and then minus.
No, del nu is not a tensor. Del nu is a symbol we use to denote the tensor you get when doing the covariant derivative on another tensor. So you should think of the whole thing, del nu v rho, as a rank 2 tensor. You can't think of del nu as its own rank 1 tensor. That's a slight ambiguity of the notation that you get used to. If we were really fastidious, we would write something like del omega nu rho. That would be the most transparent notation. Good question. Anything else? Okay. So this is a nice one. The claim is that there's two things that are equivalent. One is there exist coordinates x mu such that g mu nu equals eta mu nu everywhere on your manifold. Let's call it M for some manifold. And that is equivalent to the Riemann tensor. Vanishes everywhere. Okay? And so when either of these is true, because they're equivalent, one direction is totally obvious. If there exist coordinates where g mu nu equals eta mu nu, well, then even I can compute the Riemann tensor. Because if you go back to our formula for the Riemann tensor, it involves Christoffel derivatives and their derivatives. So their Christoffel symbols are all 0 when g mu nu is eta, and the derivatives are therefore all 0, and the Riemann tensor is 0. So going from the left one to the right one is trivial. Going the other way, Sean outlines that proof. So in this case, we say the space-time is flat. Okay? And so this really is a definition of the word flat. I've been using it freely for the whole course. But ultimately, that just comes from the fact that this same math really does describe what we call a curved surface colloquially in everyday life. Intrinsic curvature, right? Something where, on the surface of the Earth, we could tell it's curved by drawing triangles and seeing that they don't add up to 180 degrees, or drawing parallel lines and seeing that they don't stay parallel, or doing little parallel transport experiments. Those mathematical constructions do, in ordinary curved surfaces, embedded in three-dimensional space, do characterize this notion of curvature. And a flat space, has g mu nu equals, well, in this case, it would be not eta mu nu. If it's a space, it would just be the Euclidean metric with all ones, no minus ones. But in that case, we would certainly call that flat if the metric were Euclidean. And so in general, we say space-time is flat if the metric can be put in the form eta mu nu. Doesn't mean it has to be in that form. You might want to use some different coordinates for your flat space-time, which you've already done in certain calculations, at least for flat space. But if you can find coordinates where the metric is eta mu nu, then it is flat. And that's the same thing as saying the Riemann tensor as a tensor vanishes. So when I first got into relativity, my advisor told me a story. He was asked to referee a paper on a new solution of Einstein's equation. It's not easy to find solutions of Einstein's equation, especially not new ones, 100 years plus after it was written down. And as he was looking at the paper, he began to suspect that this new solution of Einstein's equation was actually flat space-time written in a funny coordinate system. And so he needed to check that it was. So how do you think he went about checking? Yeah, right. He did not. He emphatically did not try to find the coordinates that make the metric eta mu nu. This was a very complicated, solution. It was a solution. It was just flat space-time and some other coordinates. But it looked messy. It had all sorts of complicated functions of various coordinates, probably called t, x, y, z, or something like that. But it's a bit of work. You have to do that Riemann tensor calculation, right? You have to find the Christoffel symbols. Maybe for effect, I'll show the formula again. You have to find the Christoffel symbols, all of them. You have to contract them together. And you have to take these derivatives and find all of that. And you have to check every component. But he did this. He used a computer to help for this purported new solution of Einstein's equation. He found that every component was actually 0. And so you have to be a little careful when you're looking for new solutions that you don't accidentally find old solutions in new coordinates. Okay, so many of the lessons of this class are about passing from coordinate-dependent notions of what it means to be, in this case, flat. We started out by saying a flat space is one where the metric is eta mu nu. It's a coordinate-dependent notion. You should really say a flat space is one where there exist coordinates where you can make the metric eta mu nu. And now we've transitioned to a nice invariant tensorial definition. A spacetime is flat if and only if the Riemann tensor vanishes.
I have a question that might get answered. How soon are we going to talk about the Einstein's equation? You mentioned pretty soon.
I don't remember if it's this week or the next, but it's coming.
So can I ask then, is like Einstein's equation one of those things that's like actively people are still hunting for new solutions, or do people have like a list
No,
of solutions?
they're all found. I can't believe anyone's going to find anything new. You can add extra fields. You know, there's lots of people saying, what if we have Einstein's equation coupled with a scalar field with this potential and some other stuff, and now we find solutions. But vacuum Einstein equation, I can't believe anything new is going to be found.
Is that being done analytically or numerically?
Oh, numerically, you find new solutions all the time. You can take any initial data. We won't show it in the class, but Einstein's equation does have a well-posed initial value formulation. If you give the right initial data at an initial time, you can just evolve.
Oh, okay, cool.
And so then you generate new solutions at will, but they're only
So the
numerical.
analytic stuff
But yeah, the analytic stuff, I can't believe.
Okay, cool. Thank you.
I mean, you never know. But the Kerr metric of a rotating black hole was sort of a surprise. I mean, people were looking for it, but there was no reason to expect you could find an analytic solution for a rotating black hole. There's not enough symmetries. But people found it.